Moving on with section 5.2, what I want to talk about is something called identities. There are some fundamental relationships between the trig functions that can be used to help with calculation. Now, some of them we've already looked at. Things like the tangent t is equal to sine over cosine, cotangent t is then cosine over sine, secant t is equal to 1 over the cosine of t, and cosecant t is 1 over the sine of t. So those are the reciprocal identities, and they're nice, like we saw in the last lecture. If I want to compute tangent, cotangent of t, rather, secant and cosecant, I can do those by knowing the values for sine and cosine, and we talked about how I can find the values for sine and cosine by looking at my length t along the unit circle and finding that terminal point. There are 3 other identities, though, that we'll start with. We're going to be developing identities throughout the semester, but there are 3 that I think are pretty essential to developing the theory of the others. And they start with this picture. So if I look at, as per the usual, my unit circle, and I take a point on my unit circle, and I'm going to draw a triangle. Actually, let's put that in a different color so we can see it a little bit clearer. Okay, so there's my triangle. There's my length t. And t, I picked it in the first quadrant, but it doesn't really matter. I could pick it in any quadrant I want, and what I'm about to do is still going to work. Because this point, coordinates x, y, we know that the functions cosine of t and sine of t will correspond to the coordinates of that point. But what we can also see, this length here corresponds to that distance x. It forms the base of a right triangle. And this height is distance y. Forms the height of a right triangle. And being that this is a unit circle, that hypotenuse has length 1. So what I can do is use the Pythagorean theorem, which tells me that for this triangle, x, y, and 1, x squared plus y squared equals 1. So that comes from the Pythagorean theorem. This triangle here are the same. And this triangle, this distance x, the length of its base, is going to correspond to the cosine of t, no matter what t happens to be. And the height is going to correspond to this value for y, which is the sine of t. So I'm left with the identity the cosine of t squared plus the sine of t squared equals 1. And the notation that you'll see to represent this, where it doesn't cause confusion, cosine squared of t, sine squared of t equals 1. And you'll see in your text as well, they use this notation where the 2, the superscript, is right on the cosine. That's the same thing as squaring the entire thing. It's to distinguish it from the fact that the entire function value is squared rather than something that just squared the variable. Because sometimes if you write it like this and you forget to put the parentheses, it makes it look like it's just the variable that's squared. And that can be confusing when we're trying to calculate these things. So this is the preferred notation, and you'll notice that my argument here, my proof rather, for this Pythagorean theorem working out, it didn't depend on t. So this should be true no matter what length of t, what real number t you actually choose. If I start with that, cosine squared plus sine squared equals 1. There's a couple of different kind of cool things I can do. One, I can divide all three terms by cosine squared, assuming cosine is non-zero. And what I'm left with is 1 plus sine over cosine is the cotangent, and 1 over cosine is, oh, backwards. Sorry about that. Sine over cosine is the tangent, and 1 over cosine is the secant. We get another identity. Similarly, if I divide all three terms by the sine, again assuming sine is non-zero, I'm left with the cotangent squared plus 1 equals the cosecant squared. So those are my three Pythagorean identities. Those are the three that they list in your text. And sometimes these can be useful if you know one function value for one of the trig functions and you need to find the others. So suppose that I knew that cosine of t was 3/5. Now that'd be great. Cosine's representing an x-coordinate, but I could have an x-coordinate of 3/5 in quadrant 1 or quadrant 4. So let's say we're in quadrant 4. So if I'm in quadrant 4, my x values should be greater than 0, my y values should be less than 0. Now I know that sine squared of t plus cosine squared of t is equal to 1, and I can use that to find the value of the sine. Sine squared of t plus 3/5 squared is equal to 1. If you square that out and subtract, you're going to end up with sine squared t, 16 over 25. So sine of t equals plus or minus 4/5. By taking square roots, we're left with that plus and minus in front, but we know what quadrant we're in. So we know the y values have to be negative, so for this one, we're left with negative 4/5 is our appropriate value. And once we've got the sine and the cosine, that's enough. If we go back to our reciprocal identities from this first slide, we could then use the sine and cosine to find the tangent, the cotangent, the secant, and the cosecant. All of them we want. We only needed this one piece of information, what was the cosine, and one of our Pythagorean identities to find the other piece.